One of the reasons that we do control charts is to make sure everything's in control. But once everything's in control, then we can start to talk about what is our process really capable of doing. So if you remember, in the first couple of chapters, we talked about some really important questions that we needed to be able to answer. And one of them is, are we capable? Now by that we meant, does the process able to meet its requirements? So in order to be capable, first, the process has to be stable. Because if it isn't stable, we can't predict whether we'll be able to meet the requirements or not. So once the process is stable, then we can ask, does the process meet its requirements? And by meeting the requirements, what we really mean is the variation of the process within the specification limits. So part of that is going to be comparing the width of our variation with the width of the specification limits. And part of it is going to be checking to make sure that our mean is centered where it needs to be centered. So just a quick reminder of the terminology here. Process variability is the sigma that we measure in the process. And tolerance is what the specification limits give us. So tolerance is the distance from the expected value to the upper specification limit or to the lower specification limit. So in order for our process to be capable, 2t, the distance of the specifications, must be greater than or equal to the width of the process bell. And the width of the process bell is 6 sigma, 3 sigma up and 3 sigma down. So in general, we talk about 3 levels of precision, and there's not a firm cutoff between these. But generally, if 2t is a lot bigger than 6 sigma, then we say we have high relative precision. And notice here the word precision, that width of the variability. If we have high relative precision, then there's room for the process to wander a little as long as we detect it early, so we don't need to be very worried. So we say we have medium relative precision if 2t is just greater than 6 sigma. Now notice there's not a specification of what is greater than and what is a lot greater than. But medium relative precision means that our process is capable, but that capability is tenuous because small changes in the process could make us not capable. And we might not detect those changes in time to prevent shipping things that were not meeting the specifications. If 2t is less than 6 sigma, then we say we have low relative precision, which basically means we're outside the specification and the process is not capable. So we can quantify this relationship between sigma and t to be more precise about how we're measuring capability. So we should remember that if 2t is equal to 6 sigma, then about 99.7% of our output will be within tolerances. But that means 0.3% will be outside of the tolerances. And remember how these errors accumulate. If we were putting together 10 things, each of which has a 0.3% probability of being in error, remember that they go together exponentially for the likelihood that the resulting product will have a defect. So just having our process meet the tolerances may not be good enough quality. So our first measure of process capability is called the Relative Precision Index. And basically, it's hinged on this idea that we want 2t to be greater than 6 sigma. The challenge is, what value do we use for sigma? Remember, sigma is the attribute of the underlying distribution. So it is the standard deviation of the underlying distribution. But we don't have anything that measures the underlying distribution. So we know that if we're grouping data, then we can estimate sigma with the average range over Hartley's constant. So 2t over the average range has to be greater than 6 over Hartley's constant. So that gives us a relative precision index of 2t over the average range and a minimum value that tells us that we're capable. Now notice that this is assuming that our process is centered directly between the specification limits, because that's what's keeping the tails inside the tolerances. In other words, this is really only looking at precision, not accuracy. So if we use this, we need to be careful to make sure that we're checking accuracy in some other way. Our next measure of process capability is called the Cp Index. And basically, it's the ratio between the width of the tolerances and the width of 6 sigma. Just like the relative precision index, we would need some estimate of sigma, which we would probably get from average range. And this is also assuming that the process is centered within the tolerances. The nice thing about this index is all we have to do is compare it to 1 to know whether the process is capable or not. If the value is less than 1, then that means that the width between the tolerances is smaller than the width of the underlying distribution, and therefore the process is not capable. Our last measure of process capability is called the Cpk Index. And the good thing about this one is that it pays attention to variation and whether the distribution is centered or not. So we essentially compute one value for each of the specification limits, and that value compares the distance between the specification limit and the sample mean to 3 sigma, which is half the width of the distribution. The overall process Cpk will be the lower of these two values, so it's the measure that is on the worst side. Because this reflects both the centering and the width of the underlying distribution, we can make our Cpk better in 2 ways. We can either work on centering the process better, or we can work on reducing variation. So, given the definitions of Cp and Cpk, what would be true if their values were the same?